Hey, you all. Did you know that gravity might not actually be a force at all? That's right. What we've been taught since childhood, the idea that gravity pulls us down toward the Earth like an invisible string, is not quite how the universe really works. At least, not according to Albert Einstein. In fact, Einstein completely reimagined gravity, not as a force reaching across space, but as a consequence of the shape of the universe itself. This revolutionary idea forms the core of his theory of general relativity, one of the most profound and beautiful achievements in the history of physics. Now, before you drift off to sleep tonight, let your mind wander into the depths of spacetime, the four-dimensional fabric that makes up our universe, and discover why falling isn't being pulled, why planets orbit not because they're tugged by the sun, but because they're simply following the curves of reality itself. And yes, while you sleep, your brain can still absorb these deep truths about how the cosmos operates. So get comfortable, close your eyes if you'd like, and let's explore together why gravity is not a force, at least, not in the way we usually think of forces. To begin, let's go back to where most of us first encountered gravity, in the classroom, learning about Isaac Newton. Newton described gravity as a force, an attraction between any two objects that have mass. The more mass they have, and the closer they are, the stronger this force becomes. He gave us a precise mathematical rule for it. The gravitational force equals the gravitational constant times the mass of the first object times the mass of the second object, all divided by the square of the distance between them. That formula worked incredibly well for centuries. It explained why apples fall from trees, why the moon orbits the Earth, and even allowed us to send spacecraft to other planets with astonishing accuracy. But despite its success, Newton himself was uneasy about one thing. How does this force actually work? How does the Earth know to pull on the moon across 384,000 kilometers of empty space? What carries this force? Newton called this action at a distance, and he admitted he had no explanation for it. He wrote, "I frame no hypotheses about how gravity operates, it just does." For over 200 years, physicists accepted this as good enough. But Einstein wasn't satisfied. Einstein asked a deeper question. What if gravity isn't a force transmitted through space at all? What if, instead, it's something far more fundamental, something woven into the very structure of space and time? To understand this shift in thinking, we need to talk about two key ideas, the equivalence principle and the curvature of spacetime. Let's start with the equivalence principle, because it's the seed from which general relativity grew. Imagine you're inside a windowless elevator. You can't see outside, and you have no way of knowing whether you're on Earth or floating somewhere in deep space. Now, suppose the elevator is sitting still on the surface of the Earth. You feel your weight pressing down on the floor. If you drop a pen, it falls straight down and hits the ground. Everything behaves exactly as you'd expect under gravity. But now imagine a different scenario. The elevator is in deep space, far from any planet or star, and a rocket attached to the bottom is accelerating upward at 9.8 meters per second squared. That's the same rate at which objects accelerate due to gravity on Earth. Inside this accelerating elevator, you'd also feel pressed against the floor. If you let go of the pen, the floor would rush up to meet it, making it appear as though the pen is falling downward. To you, inside the elevator, there would be no experiment you could perform to tell the difference between being in a gravitational field on Earth and being in an accelerating spaceship in empty space. This is the equivalence principle. The effects of gravity are locally indistinguishable from the effects of acceleration. In other words, standing still in a gravitational field feels exactly the same as accelerating through empty space. This simple but powerful insight led Einstein to a radical conclusion. If gravity and acceleration are equivalent, then maybe gravity isn't a force at all, but rather a feature of how we experience motion in curved spacetime. Now, what do we mean by spacetime? Before Einstein, space and time were thought of as separate and absolute. Space was the three-dimensional stage, length, width, and height, on which events happened, and time was a universal clock ticking the same for everyone everywhere. But Einstein's earlier theory, special relativity, already showed that space and time are not independent. They are interwoven into a single four-dimensional continuum called spacetime. In this view, every event, whether it's a firecracker exploding or a bird taking flight, is a point in spacetime, specified by three spatial coordinates and one time coordinate. Special relativity also revealed that time can slow down, and lengths can contract depending on how fast you're moving relative to someone else. But crucially, special relativity only applies in the absence of gravity, in flat spacetime, where no masses are present to warp the geometry. General relativity extends this framework to include gravity. Einstein proposed that mass and energy, since they are equivalent, cause spacetime to curve. And what we perceive as gravity is simply the effect of objects moving along the straightest possible paths through this curved spacetime. Weight straightest possible paths in curved space. That might sound contradictory, but it's a key concept. In ordinary flat geometry, the shortest path between 2 points is a straight line. But on a curved surface, like the surface of the Earth, the shortest path is a curve called a geodesic. For example, airplanes flying from New York to Tokyo don't follow a straight line on a flat map. They follow a great circle route, which is the geodesic on the sphere of the Earth. It looks curved on a flat map, but it's actually the straightest possible path on the globe. Similarly, in curved spacetime, freely moving objects, those not acted upon by any real forces, follow geodesics. These are the spacetime equivalents of straight lines. So when you drop a ball, it's not being pulled down by a force. Instead, it's moving along a geodesic in spacetime that's been curved by the presence of the Earth's mass. From your perspective standing on the ground, it looks like the ball is accelerating downward. But in reality, the ball is in free fall, moving inertially, just as a spaceship coasting through empty space would. It's you, standing on the Earth, who is being pushed upward by the ground, preventing you from following your own natural geodesic path toward the center of the Earth. This is why astronauts in orbit feel weightless. They're not beyond Earth's gravity. Gravity at the altitude of the International Space Station is still about 90% as strong as it is on the surface. But they're in free fall, continuously falling toward Earth while also moving sideways so fast that they keep missing it. They're following a geodesic in curved spacetime, and because nothing is pushing against them, they experience no sensation of weight. In their reference frame, there is no gravity, only smooth, unforced motion. So to restate, gravity is not a force that acts on objects. Instead, massive objects like stars and planets warp the geometry of spacetime around them, and other objects simply move along the straightest paths available in that warped geometry. What looks like gravitational attraction is really just geometry in action. Now, how do we describe this mathematically? Einstein spent nearly a decade developing the equations that link the curvature of spacetime to the distribution of mass and energy. The result is the Einstein field equations, one of the most elegant and complex sets of equations in all of physics. At its core, the Einstein field equation states that the curvature of spacetime on the left-hand side equals a quantity related to the energy and momentum of matter and radiation on the right-hand side. Written out in words, it says, the Einstein tensor equals 8 pi times the gravitational constant divided by the speed of light to the 4th power, all multiplied by the stress energy tensor. Let's unpack that slowly. The Einstein tensor describes how spacetime is curved. It encodes information about the geometry, such as how volumes change and how initially parallel geodesics converge or diverge. The stress energy tensor, on the other hand, describes what's in spacetime, not just mass, but also energy, pressure, momentum flow, and stress. Because of Einstein's famous equation E equals mc squared, mass and energy are interchangeable, so both contribute to curving spacetime. The constants in front, 8 pi, the gravitational constant, and the speed of light to the fourth power, are there to make the units match and to ensure that in weak gravitational fields like those on Earth, general relativity reduces to Newton's law of gravity. This is crucial. Any new theory must reproduce the successes of the old one in the appropriate limits. And indeed, when spacetime is only slightly curved and speeds are much slower than light, Einstein's equations give results almost identical to Newton. But in extreme conditions, near black holes during the Big Bang, or in the precise orbit of Mercury, general relativity makes predictions that differ from Newton's, and every experimental test so far has confirmed Einstein's version. Take Mercury, for example. Newtonian gravity, even when accounting for the gravitational tugs from other planets, couldn't fully explain a tiny anomaly in Mercury's orbit called the precession of its perihelion. Every century, Mercury's closest point to the Sun shifts by about 56/100ths of a degree more than Newton predicts. For decades, astronomers puzzled over this. Some even suggested there was an unseen planet, Vulcan, orbiting inside Mercury's path. But Einstein showed that general relativity naturally accounts for this extra precession, because near the Sun, spacetime is significantly curved, and Mercury's orbit follows a geodesic in that curved geometry. No extra planet needed. When Einstein calculated the value and saw it matched observation exactly, he reportedly had heart palpitations from excitement. Another dramatic confirmation came in 1919 during a solar eclipse. Einstein predicted that light, though massless, should bend as it passes near a massive object like the Sun, because light also follows geodesics in curved spacetime. British astronomer Arthur Eddington led an expedition to measure the positions of stars near the Sun's edge during the eclipse. The results showed that starlight was deflected by precisely the amount Einstein predicted, twice as much as Newtonian gravity would suggest if you treated light as particles with mass. Overnight, Einstein became a global celebrity. Since then, we've seen countless other validations. Gravitational time dilation. Clocks run slower in stronger gravitational fields. The existence of black holes, gravitational waves rippling through spacetime from colliding neutron stars, and even the precise timing needed for GPS satellites to function, all require corrections from general relativity to work accurately. But let's return to the core idea. If gravity isn't a force, why do we feel it? Why do we say we weigh so many pounds or kilograms? The answer lies in what's preventing us from following our natural geodesic path. When you're standing on the ground, the Earth's surface is pushing up on your feet with a force equal to what Newton would call your weight. This upward force from the ground is a real force. It's electromagnetic in origin, arising from the repulsion between the electrons in your shoes and the electrons in the floor. It's this force that you feel as weight, not gravity itself. In contrast, when you're in free fall, like skydiving before air resistance becomes significant, you feel weightless because nothing is pushing against you. You're moving along your geodesic, and in your local frame of reference, there is no gravity. This is why Einstein called gravity a pseudo-force, or fictitious force, similar to the centrifugal force you feel when going around a curve in a car. That outward push isn't a real force acting on you. It's an artifact of being in an accelerating or rotating reference frame. Likewise, gravity arises because we're using a non-inertial reference frame, standing on a planet that's preventing us from falling freely. Now let's consider a deeper implication. Time itself is affected by gravity. In general relativity, spacetime isn't just curved in space, it's curved in time as well. Clocks tick slower in stronger gravitational fields. This isn't a mechanical defect in the clocks, it's a fundamental property of time. Near a massive object, the time dimension of spacetime is stretched, so processes, including aging, occur more slowly relative to someone in weaker gravity. For example, a clock at sea level runs slightly slower than a clock on a mountain top, because gravity is stronger closer to Earth's center. This effect has been measured with atomic clocks accurate to nanoseconds. GPS satellites, orbiting about 20,000 kilometers above Earth, experience weaker gravity, so their clocks run faster than clocks on the ground by about 45 microseconds per day. If engineers didn't correct for this, and also for the time-slowing effect of their orbital speed from special relativity, GPS locations would drift by kilometers each day. So your phone's navigation system literally depends on Einstein's theory being correct. This intertwining of space and time means that gravity affects not just where things go, but when they happen. The curvature of spacetime dictates the entire history of motion, past, present, and future, for every particle and beam of light in the universe. Let's visualize spacetime curvature with a common analogy, the rubber sheet. Imagine stretching a flat, taut rubber sheet horizontally. Now place a heavy ball, like a bowling ball, in the center. It creates a dip or well in the sheet. If you roll a marble nearby, it will spiral inward toward the bowling ball, not because the bowling ball is pulling it with a force, but because it's rolling along the curved surface. The marble is following the geometry of the sheet. This analogy is helpful, but it has limitations. First, it uses gravity, Earth pulling the balls down, to simulate gravity, which is circular. Second, it only shows curvature in 2 spatial dimensions, while real spacetime has 3 spatial dimensions plus time. Most importantly, it doesn't capture how time is curved, which is actually the dominant effect in most gravitational situations, like on Earth. In fact, for slow-moving objects in weak gravity, the warping of time contributes far more to what we perceive as gravity than the warping of space. The reason you fall toward Earth is primarily because time flows slower closer to the ground. Your head ages slightly faster than your feet, and objects naturally move toward regions where time runs slower. This tendency manifests as what we call gravitational attraction. To see why, consider the principle of least action, or, more intuitively, the idea that objects seek paths that maximize their proper time, the time measured by a clock moving with them. In flat spacetime, the path of maximum proper time between 2 events is a straight line at constant velocity. But in curved spacetime near a planet, the path that maximizes proper time actually curves toward the mass, because spending more time in a region where time runs slower reduces the total, elapsed proper time less than you might expect. The mathematics shows that this optimization leads directly to the trajectories we observe. So again, no force is involved, just geometry and the nature of time itself. Now, what about black holes? These are regions where spacetime curvature becomes so extreme that nothing, not even light, can escape once it crosses a boundary called the event horizon. According to general relativity, if you compress enough mass into a small enough volume, spacetime curves so severely that all future directed paths inside the horizon lead toward the center, a point of infinite density called a singularity. From far away, a black hole's gravity behaves just like any other mass of the same size. Planets could orbit a black hole just as they orbit a star. But up close, the curvature dominates. Time slows to a crawl near the event horizon from an outsider's perspective, and space becomes so twisted that forward in time points inexorably toward the singularity. Black holes are not just theoretical. They've been observed indirectly for decades through their effects on nearby stars and gas. And directly in 2019, when the Event Horizon Telescope captured the shadow of a supermassive black hole in the galaxy M87. The image matched general relativity's predictions with stunning precision. Even more recently, detectors like LIGO and Virgo have observed gravitational waves, ripples in spacetime itself, produced when black holes or neutron stars spiral into each other and merge. These waves travel at the speed of light, stretching and squeezing space as they pass. Their detection confirmed another key prediction of Einstein's theory and opened a new window on the universe. All of this stems from the simple but revolutionary idea that gravity is geometry. Let's revisit Newton for a moment. In Newtonian physics, force equals mass times acceleration. More precisely, the acceleration of an object equals the net force acting on it divided by its inertial mass. So, acceleration equals force pull divided by mass inertial. But there's another kind of mass, gravitational mass, the property that determines how strongly an object feels and sources gravity. Experimentally, inertial mass and gravitational mass are always equal, to incredible precision. This is why all objects fall at the same rate in a vacuum, regardless of their mass or composition, as Galileo supposedly demonstrated by dropping weights from the Leaning Tower of Pisa. Newton treated this equivalence as a coincidence, but Einstein elevated it to a principle, the equivalence principle, and made it the foundation of his theory. If gravitational mass equals inertial mass, then gravity affects everything the same way, just like acceleration does. And that's exactly what you'd expect if gravity isn't a force acting on objects, but a property of the stage on which they move. In general relativity, there's no need to distinguish between gravitational and inertial mass. They're the same because gravity isn't a force that couples to mass. It's the curvature of spacetime that everything moves through. This also explains why light, which has no mass, is still affected by gravity. In Newton's theory, a massless particle wouldn't feel gravity at all. But in Einstein's view, light follows geodesics in spacetime, and if spacetime is curved by a star, the light bends, even though it has no mass. This was one of the first dramatic confirmations of general relativity, as we mentioned earlier. Now, let's think about the universe as a whole. General relativity isn't just about planets and stars. It's the framework for modern cosmology. Einstein's equations describe how the entire universe evolves. When applied to the cosmos on large scales, assuming it's roughly uniform and isotropic, the same in all directions, the equations predict that the universe must either expand or contract. Einstein initially resisted this, adding a cosmological constant to force a static solution, but later called it his greatest blunder when Edwin Hubble discovered in 1929 that galaxies are receding from us, proving the universe is expanding. Today, we know the expansion is accelerating, driven by something we call dark energy, which may actually be Einstein's cosmological constant after all, representing a constant energy density of the vacuum. So even his mistake turned out to be prescient. On the largest scales, spacetime itself is dynamic, stretching, evolving, and carrying galaxies apart like raisins in rising dough. Gravity, in this grand view, shapes the fate of the cosmos, whether it will expand forever, eventually collapse, or tear itself apart in a big rip. All of this emerges from the geometry of spacetime responding to its contents. But back to everyday experience. Why does this matter to you? Because it changes how you see reality. You're not being pulled down by a mysterious force. You're standing on a planet that's warping the four-dimensional fabric of the universe, and your natural path would be to fall freely along a geodesic toward its center. The floor stops you, and that's what you feel. The sky isn't empty. It's a dynamic, flexible entity that bends, ripples, and flows. And when you look up at the stars, remember, their light has traveled for years, centuries, or millennia along geodesics in curved spacetime, bent by galaxies and clusters along the way, bringing you messages from the distant past, shaped by the geometry of the cosmos. So tonight, as you lie in bed, imagine spacetime around you, not as a static void, but as a living, breathing structure, gently curved by the Earth beneath you, by the Moon overhead, by the Sun 150 million kilometers away. And know that you, too, are part of this grand geometry, your mass contributing, however minutely, to the shape of the universe. Gravity isn't a force reaching out to grab you. It's the universe telling you how to move. And with that, let your thoughts settle, your breathing slow, and your mind float freely along its own geodesic, through the quiet curvature of spacetime as you drift into sleep. As you continue to drift in that quiet space between wakefulness and sleep, let's deepen our journey into the heart of Einstein's vision. We've established that gravity isn't a force like magnetism or friction. It's the curvature of spacetime itself. But how exactly does mass curve spacetime? And what does curved spacetime really mean when we can't see it or touch it? To answer this, we need to move beyond analogies like the rubber sheet and confront the true nature of geometry. Not just the flat, Euclidean geometry you learned in school, but a more flexible, dynamic kind called differential geometry. In this framework, curvature isn't something imposed from outside. It's an intrinsic property of space itself, detectable by measurements made entirely within that space. Imagine you're a two-dimensional being living on the surface of a sphere, like an ant crawling on a globe. You have no concept of up or down. Your entire universe is the surface. If you walk in what feels like a straight line, you'll eventually return to your starting point. If you draw a triangle by connecting 3 points with the straightest possible paths, great circles, you'll find that the angles add up to more than 180 degrees. On a flat plane, they'd always sum to exactly 180. This excess is a direct measure of the sphere's intrinsic curvature. Similarly, in our four-dimensional spacetime, curvature reveals itself through the behavior of geodesics. In flat spacetime, two objects moving parallel to each other will stay parallel forever. But in curved spacetime near a massive object, initially parallel geodesics converge. That's why two apples dropped side by side toward Earth don't fall on perfectly parallel paths. They very slightly move toward each other as they fall, because their geodesics are curving toward the Earth's center. This convergence is tidal gravity, the same effect that causes ocean tides, and it's the true signature of spacetime curvature. Newton described tides as the result of differences in gravitational force across an extended object. The moon pulls harder on the side of Earth closest to it than on the far side, stretching the oceans. But in general relativity, there's no force at all. Instead, different parts of Earth follow slightly different geodesics through curved spacetime, and the relative acceleration between them creates the tidal bulge. So even tides are geometry in motion. Now, let's return to the Einstein field equations, the mathematical core of general relativity. Earlier, we said the equation states that the Einstein tensor equals 8 pi times the gravitational constant divided by the speed of light to the fourth power, multiplied by the stress-energy tensor. But what do these tensors actually represent? A tensor is a mathematical object that generalizes scalars and vectors, while a scalar is just a number like temperature, and a vector has magnitude and direction like velocity. A tensor can describe more complex relationships, like how pressure in one direction affects strain in another. In general relativity, tensors are essential because they allow equations to hold true for all observers, regardless of their motion or coordinate system. This is the principle of general covariance. The laws of physics must take the same form in every reference frame. The stress-energy tensor, often denoted T sub mu nu, encodes everything that contributes to gravity: energy density, momentum density, pressure, and shear stress. For a perfect fluid, a good model for stars or the early universe, it includes the energy density and isotropic pressure. Even light, which has no rest mass, carries energy and momentum, so it contributes to the stress-energy tensor and thus curves spacetime. This is why a box full of photons weighs more than an empty box, because energy gravitates. On the left side, the Einstein tensor, G sub mu nu, is built from the Ricci curvature tensor and the Ricci scalar, which themselves come from the Riemann curvature tensor. The Riemann tensor is the most complete description of spacetime curvature. It tells you how a vector changes when you parallel transport it around a small loop. If spacetime is flat, the vector returns unchanged. If curved, it comes back rotated or stretched. The Ricci tensor is a contraction of the Riemann tensor, summarizing how volumes change due to curvature. The Ricci scalar is a further contraction, giving a single number representing average curvature at a point. Einstein cleverly combined these into the Einstein tensor so that its divergence is zero, ensuring local conservation of energy and momentum, just as required by physics. This was no small feat. It took him years of false starts and collaboration with mathematicians like Marcel Grossmann to find the right form. The resulting equation is nonlinear, which makes it incredibly difficult to solve. Unlike Newton's gravity, where you can simply add the effects of multiple masses, in general relativity, the gravitational field itself carries energy and thus generates more gravity. This self-interaction means spacetime curvature begets more curvature, leading to rich phenomena like black holes and gravitational waves, but also making exact solutions rare. Only a handful of exact solutions are known. The simplest is the Schwarzschild solution, discovered in 1916 by Carl Schwarzschild just months after Einstein published his theory. It describes the spacetime outside any spherical, non-rotating mass, like a star or a black hole. The Schwarzschild metric tells us precisely how time and space are distorted near such an object. For example, the time component of the metric shows that clocks run slower closer to the mass. Specifically, the rate of a clock at radius r compared to one at infinity is given by the square root of 1 minus 2 times the gravitational constant times the mass divided by the speed of light squared times. When r equals 2 gm over c squared, this factor becomes 0. Time appears to stop from a distant observer's view. This radius is the event horizon of a Schwarzschild black hole. Inside the horizon, the roles of time and space swap. The radial direction becomes time-like, meaning falling toward the singularity is as inevitable as moving forward in time. You can no more avoid the center than you can avoid next Tuesday. But real astrophysical black holes rotate, so the more realistic solution is the Kerr metric, found in 1963. Rotation drags spacetime around with it, a phenomenon called frame dragging. Near a spinning black hole, space itself is twisted into a vortex. This effect has been measured around Earth by satellites like Gravity Probe B, which detected tiny shifts in gyroscopes, orientation due to our planet's rotation warping local spacetime. Frame dragging illustrates another key point. It's not just mass that curves spacetime, but also momentum and angular momentum. The stress-energy tensor includes these, so moving matter creates additional curvature beyond what static mass would produce. Now, consider gravitational waves, ripples in spacetime curvature propagating at the speed of light. They're generated when masses accelerate asymmetrically, like two black holes orbiting each other. As they spiral inward, they lose energy by radiating gravitational waves, causing their orbit to shrink until they merge in a violent burst of spacetime vibrations. These waves stretch and compress space perpendicular to their direction of travel. When a wave passes through Earth, it alternately squeezes space in one direction while stretching it in the other, then vice versa. Detectors like LIGO use laser interferometry to measure these tiny distortions, changes in distance smaller than 1/10,000th the width of a proton. The first direct detection in 2015 confirmed a prediction made a century earlier and opened gravitational wave astronomy. We can now hear the universe through spacetime itself, observing collisions invisible to light-based telescopes. All of this stems from the idea that spacetime is not a passive stage, but a dynamic participant in physics, bending, vibrating, and evolving in response to its contents. Let's now address a common question. If spacetime is curved, what is it curved into? This is a natural question if you're picturing the rubber sheet analogy, where the sheet bends into a third spatial dimension. But in general relativity, spacetime doesn't need to be embedded in a higher dimensional space to be curved. Its curvature is intrinsic, defined entirely by measurements within it, like the triangle angles on a sphere. We don't need a fifth dimension for spacetime to curve. The mathematics describes curvature using only the 4 dimensions we have. This is a profound shift from everyday intuition. We're used to thinking of curvature as extrinsic, something visible from outside. But the universe has no outside. Spacetime is all there is, and its geometry is self-contained. Another subtle point. In general relativity, there are no global inertial frames, only local ones. In special relativity, you can find reference frames covering all of spacetime where objects move at constant velocity unless acted upon by forces. But in curved spacetime, inertial motion is only straight over small regions. Over larger distances, geodesics deviate due to curvature. So the best you can do is define a local inertial frame at each point, a small free-falling lab where, for a brief time in space, gravity disappears and special relativity holds. This is why the equivalence principle is local. It only works in regions small enough that tidal effects are negligible. In a large elevator near Earth, you'd notice apples falling toward the center, not parallel paths, revealing the curvature. Now, let's consider energy in general relativity. In Newtonian physics, gravitational potential energy is well defined. It's negative and becomes more negative as objects get closer. But in general relativity, there's no universal way to define the gravitational energy of a system. Because gravity is geometry, not a force field, you can't localize gravitational energy the way you can with electromagnetic energy. The stress-energy tensor includes all non-gravitational energy, but gravitational energy itself isn't part of it. It's encoded in the curvature on the left side of Einstein's equation. This leads to puzzles like the fact that the total energy of a closed universe might be 0. The positive energy of matter and motion is exactly balanced by the negative gravitational potential energy. Some cosmologists suggest the entire universe could be a free lunch, a quantum fluctuation where total energy sums to 0. Speaking of quantum physics, we must acknowledge that general relativity is a classical theory. It doesn't incorporate quantum mechanics, and at extremely small scales, like the Planck length, 10 to the minus 35 meters, quantum effects should dominate gravity. We don't yet have a complete theory of quantum gravity, though candidates like string theory and loop quantum gravity are being explored. In black hole singularities and the Big Bang, both quantum mechanics and strong gravity are important, so our current theories break down. Resolving these requires unifying Einstein's geometric gravity with quantum principles, a major unsolved problem in physics. But for almost all observable phenomena, from GPS to galaxy clusters, general relativity reigns supreme. Let's revisit the experience of falling. Suppose you jump off a diving board. From your perspective, you're weightless. You float, your arms drift freely, and if you release a water bottle, it hovers beside you. There's no sense of up or down. In your local inertial frame, spacetime is flat, and you're moving inertially along a geodesic. But to someone standing on the pool deck, you're accelerating downward at 9.8 meters per second squared. Who's right? Both are. Because in relativity, motion is relative, and there's no privileged frame. However, your frame is locally inertial. Theirs is not, because the ground is pushing them upward, deviating them from their geodesic. This highlights a deep philosophical shift. In Newtonian physics, acceleration is absolute. You can tell if you're accelerating by feeling fictitious forces. But in general relativity, even acceleration is relative to the local spacetime geometry. Free fall is the natural state of motion. Deviation from it requires a real force. So when you stand on Earth, you are constantly accelerating upward, relative to local inertial frames, at 9.8 meters per second squared. This may sound paradoxical, but it's consistent. Your world line through spacetime is curved, not straight, because the electromagnetic force from the ground prevents you from following the geodesic. In spacetime diagrams, your path curves upward in time, while a falling object's path is straighter. The curvature of your world line is what you feel as weight. Now consider light again. Since light always travels at the speed of light, its path through spacetime is called a null geodesic. Null because the spacetime interval along it is zero. In curved spacetime, these null geodesics bend, causing gravitational lensing. Massive galaxies can act as lenses, distorting and magnifying light from objects behind them, creating arcs, rings, or multiple images. Astronomers use this effect to map dark matter, which doesn't emit light but curves spacetime through its gravity. By analyzing how background light is bent, we infer the distribution of mass, revealing cosmic structures invisible otherwise. This demonstrates that gravity, as spacetime curvature, is the primary tool for probing the universe's mass content, even when that mass is hidden. Let's also clarify a frequent misconception. General relativity doesn't disprove Newton. It supersedes him, just as Newton superseded Aristotle. Newton's laws are an excellent approximation when gravity is weak and speeds are slow compared to light. Engineers use Newton to build bridges and send probes to Mars because the corrections from general relativity are tiny in those regimes. But for precision cosmology, black holes, or GPS, Einstein is essential. Science progresses by expanding the domain of accurate description, not by discarding old truths where they still apply. Now imagine two astronauts floating in deep space, far from any mass. They're at rest relative to each other. If nothing acts on them, they'll remain at rest, following straight geodesics in flat spacetime. But now suppose a massive object suddenly appears between them, ignoring how it's a thought experiment. Spacetime curves, and their geodesics now bend toward the mass. From their perspective, they start moving toward each other and the mass, even though no force acts on them. Their relative acceleration is purely due to spacetime geometry. This is gravitational attraction without force, just initial conditions and geodesic motion in curved spacetime. What determines the shape of spacetime? The distribution of mass and energy via Einstein's equations. But solving those equations for realistic situations is hard. For the solar system, we use approximations like the post-Newtonian expansion, which adds small relativistic corrections to Newtonian orbits. For binary pulsars, neutron stars orbiting each other, we can calculate orbital decay due to gravitational wave emission with stunning accuracy, matching observations to within 0.1%. The Hull-Staler binary pulsar, discovered in 1974, provided the first indirect evidence for gravitational waves. Its orbital period decreases exactly as predicted by general relativity, as it loses energy to ripples in spacetime. This earned Hulse and Taylor the 1993 Nobel Prize. Direct detection came decades later with LIGO, but the theory had already passed this test with flying colors. Now let's think about time again. In general relativity, time is not universal. Each observer has their own proper time, measured by a clock they carry. The flow of time depends on both motion, from special relativity, and gravity, from general relativity. Near a black hole, time dilation becomes extreme. To a distant observer, an object falling in appears to slow down and fade as it approaches the event horizon, never quite crossing it. But from the falling object's perspective, it crosses the horizon in finite proper time and continues toward the singularity. Both descriptions are correct within their own reference frames. There's no contradiction, just different ways of slicing spacetime into space and time. This relativity of simultaneity is even more pronounced in curved spacetime. Events that are simultaneous for one observer may not be for another, and global time ordering can break down near strong gravity. Yet causality is preserved. No signal can travel faster than light, so cause always precedes effect in every local frame. Now, consider the cosmological implications once more. The Friedmann equations, derived from Einstein's field equations for a uniform universe, describe how the scale factor of the universe changes with time. The scale factor tells us how distances between galaxies grow as space expands. Initially, Einstein added the cosmological constant, a repulsive term to keep the universe static. But when Hubble found expansion, Einstein abandoned it. However, in 1998, observations of distant supernovae revealed that expansion is accelerating, implying a repulsive component, now called dark energy. The simplest explanation is Einstein's cosmological constant, a constant energy density of the vacuum. Vacuum energy, predicted by quantum field theory, should curve spacetime, but theoretical estimates of its value are off by up to 120 orders of magnitude, a major puzzle known as the cosmological constant problem. Still, observationally, dark energy behaves like a cosmological constant, making up about 68% of the universe's energy content. The rest is dark matter, 27%, and ordinary matter, 5%. All of this is inferred through gravity, through how spacetime curves on cosmic scales. So even the largest mysteries of modern cosmology are rooted in Einstein's insight that gravity is geometry. Let's return to your daily life. When you step on a scale, it measures the normal force, the upward push from the scale balancing the tendency of your geodesic to curve toward Earth's center. That force equals your mass times the acceleration due to gravity, or m times g, but in general relativity, g isn't a fundamental constant of force. It's a measure of how much spacetime curves per unit mass. The gravitational constant g appears in Einstein's equations as a coupling strength between matter and geometry. A larger g would mean the same mass curves spacetime more strongly, leading to stronger gravity. But fundamentally, your weight is the resistance to free fall. In orbit, that resistance vanishes, so you're weightless, even though Earth's gravity is still shaping your path. This is why astronauts train in vomit comet airplanes that fly parabolic arcs. At the top of the arc, the plane is in free fall, simulating weightlessness inside. For about 25 seconds, everyone and everything floats, not because gravity is gone, but because they're all following the same geodesic. It's a beautiful demonstration that gravity is not something that acts on you. It's the shape of your path through spacetime. Now imagine a universe with no matter or energy. Then the stress-energy tensor is zero everywhere. Einstein's equations reduce to the Einstein tensor equals zero, which implies spacetime is flat, Minkowski space, the arena of special relativity. No curvature, no gravity. Add a single particle and spacetime curves around it. The particle doesn't emit gravity. Its presence defines the local geometry. Other particles respond not to the source, but to the geometry at their location. This locality is crucial. In general relativity, objects only respond to the curvature of spacetime right where they are. There's no action at a distance. Changes in curvature propagate at the speed of light as gravitational waves, preserving causality. Newton's gravity, by contrast, is instantaneous, violating relativity. Einstein fixed this by making gravity local and causal. So when the sun moves, Earth doesn't feel it instantly. It continues orbiting the point where the sun was about 8 minutes ago, the light travel time, until the change in spacetime curvature reaches us. This delay is built into the field equations. Finally, let's reflect on the elegance of this theory. With a single principle, the equivalence of gravity and acceleration, and a deep respect for the unity of space and time, Einstein rebuilt our understanding of the cosmos. He showed that the motion of planets, the bending of starlight, the ticking of clocks, and the evolution of the universe all stem from one idea. Mass tells spacetime how to curve. Spacetime tells mass how to move. That famous summary, often attributed to physicist John Wheeler, captures the essence. There's no separate law for orbits, no extra rule for light bending, just geodesics in curved geometry. And as you lie there now, perhaps half asleep, remember that you are not separate from this grand structure. Your body, your breath, the air around you, all contribute minutely to the stress-energy tensor, all participate in the curvature of spacetime. You are not just in the universe, you are of it, woven into its geometric fabric. Gravity isn't pulling you down. The Earth is rising up to meet you through the curvature it creates in time itself. So rest easy, knowing that your natural state is free fall, and every night as you surrender to sleep, you're aligning with the deepest truth of motion in our universe. You are following your geodesic through the silent, starlit curves of spacetime, as the cosmos hums its quiet song of geometry, and you drift deeper. Good night, sleep well, and may your dreams follow the gentle geodesics of spacetime.